Okay, let's look at temperature versus heat. Everyone has a qualitative understanding of temperature. It's the quantitative aspect that gets us. So we feel differently at different temperatures. But nerves best inform us of the differences, but it is not exact. Okay, I reached into a 400-degree oven yesterday, 400 Fahrenheit, of course, and it was not overly hot until my finger slipped off the insulating a pad that I was using, and I touched the 400-degree Fahrenheit Pyrex dish on the side. Why did my finger suddenly feel a lot hotter enough to make me move my finger? Well, the air and the rack are the same temperature, but they have a very different energy constituents and the ability to transfer heat. There was conduction going on, and that's why you put things in the oven, because there is conduction. It heats it up. There's radiation going on. I could feel that energy coming in from the side, and that was directional. In this case, hands towards the center, the back of the hands were hotter than the front of the hands, which of course had heat pads on them. But I became a very highly efficient thermal conductor when I touched that Pyrex dish. And it didn't burn myself. You move yourself away fairly quickly when you feel that. But that's heat versus temperature, and the transfer of heat, or radiation and convection, versus conduction. When you touch something, you become the conductor, and it's true with the electricity also, so be careful. But you become the conductor, and humans are very good conductors of heat. They're also very good emitters and very good radiation absorbers as well. To understand the laws of thermodynamics, it's helpful to understand the internal energy of a system and how it's changed. So let's review those laws one more time. The zeroth law is that energy always seeks equilibrium. The first law, per joule, energy is not now being created or destroyed, or the total energy in a system is constant. The second law, energy always flows down a thermodynamic gradient. In other words, entropy always increases, or it always moves from the hotter to the colder. There's lots of ways of seeing that. Work done by the system. There's some loss in every energy transaction. There's some energy lost in the transaction itself. If you remember, some time ago we looked at a power supply and the fan. The fan was just, its job is to move air through that system and extract the heat out of the system via the air. So in that case, it was radiated heat from the system itself, heating up the air, so that's Carnot, and then extracting that, moving it out of the way as you move that fluid we call air, atmospheric air, out of that device. But there's some heat loss, so it looked hot. It's all the second law of thermodynamics. It's flowing down a thermodynamic gradient. The third law is that at 0 degrees Kelvin, entropy is also 0 Kelvin, or the entropy of a system approaches a constant value of 0, actually, as the temperature approaches 0. So there's less and less entropy as you approach 0. The colder it gets, the less work can be done, right? Heat is energy that moves into or out of a system because of a temperature difference between the systems and their surroundings. Work, on the other hand, is the energy exchange that results when the force F moves through an object at a distance d. So work equals F. Equals F times d, or force times distance. Again, the subject is, how does thermodynamics apply to heat transfer, in our case, into thermal imaging or thermography? Okay, well, there are three methods of heat transfer. That is conduction. We just talked about that a minute ago with my finger touching the Pyrex dish. The transfer of heat between two parts of a stationary system caused by a temperature difference between the parts. Transmission through a conductor. So my finger became the conductor. So the vibrating energy of the particles, some was being given off as infrared light. It was convecting, conducting, but my finger became part of that and conducted that heat. Thermal conductivity is the ability of a substance to transmit heat to another physical part or another physical object. It depends on the atomic or molecular structure and the physical state the mass is in at the time. Quite literally, it is the passing of heat by molecular collision with adjacent molecules. Your nerves sense those collisions. Things are speeding up inside. Your finger says this is hot. Your neurological response is move your finger. Okay. The second method of heat transfer is convection. Again, back to the oven. That's why you put things into an oven. It creates that heat. Carnot says it's radiating out and heating other things, and also it convects. It moves air around in that oven. Now, a convection oven is a little bit different in that it actually moves the air, and that helps to transmit that heat even faster by moving the air itself around inside the oven. Okay, convection is the transfer of heat by circulation or movement of the heated parts of a liquid or a gas, that is fluids. The change in the density causes molecules that are warmed in the fluid to rise up and the cooler molecules to drop down. Again, the molecules bump into each other, speeding up one and slowing down the other as the heat is transferred. When it's transferred to a physical mass, like let's say the Pyrex dish or the food that was in it, it translates back into molecular motion, where those molecules are bumping into each other. Okay. Radiation is the opposite process. That is, it's when heat conducts out to the surface, some of that energy, it is emitted as infrared particles or other particles. Hopefully what you're seeing is not above the infrared, or that is below the wavelength of infrared. It would mean it was a lot hotter. We have seen those, though. There are stories we can tell you about ships and other objects that have been glowing red. They were so hot. In other words, the wavelength shortened into the red range, and we could see it with our eyes. But radiation is the process wherein energy is emitted as particles, light energy. Thermal energy is transferred through a medium to a different object by absorption of electromagnetic radiation, such as the Earth receives 1.4 kilowatts of energy per meter by radiation from the sun. So the radiation, the percentage of energy emitted is called emissivity. It's the process of emitting. It is expressed as it's a dimensionless number. That is, there's not a dimension. It's not time or not time or distance, but it's a ratio, and it's usually expressed as a decimal. Up to 1, of course. 1 would be 100%. If it was over 1, you'd be you'd have cold fusion. You'd have something that doesn't actually happen. You'd have more energy being emitted than contained. The box pictured here is an evaporation condensation desalination unit at San Diego State University, where I was an adjunct faculty member. This is one of my projects. I was the principal investigator of this project and others. This device is radiating energy, which is apparent to us all. You can see it in the thermogram, but it is also convecting inside, which is so it's making clean water from the salt water. That is, its evaporation condensation is distillation, so it's making distilled water. The salt water is entering in the unit and coming out as very pure water. But let's treat this image for a second as if it were a solid block, which is conducting energy through it, then to the surface. Note the arrows are coming through the image itself. The mass, A, is passing heat through it, which is the blue arrows indicating, and this conduction of heat through the mass. And only then the energy is striking the surface and being emitted from that surface as radiation. The conduction itself can be described as the rate of heat flow through that mass. Since this is a rate, it is divided by time, and since time is a dimension, it's not a dimensionless number, so we have the Q over T, which equals time, okay? That rate is the thermal conductivity of the mass multiplied by the contact area if we were conducting from one mass to another, as it is frequently the case, and actually is here, since this is a box made out of 316L stainless steel, and you can see the hot edge, let's say right in the center or at the top and on the left. Those are edges or corners. There's other ones here, but those are edges or corners you can see, and where actual conduction is taking place. Okay, and so it is that you multiply that by the difference in the temperature in Celsius and divide by the thickness of the mass itself to understand the conductivity of this. And you can get fairly complex in thermography, but it's not always necessary. But when you're presented with a complex picture, you need to understand where that energy is coming from, how it conducts, how it convects, and how it radiates and from one into another. Let me show you what I mean.